Hi, my name is Juan Carlos Saez, and I am an associate professor at the Complutense University of Madrid. In this video, I will present our article entitled Contention-Aware for Scheduling for Asymmetric Single ISA Multicore Systems. This work has been selected as the featured article of the month for the 2018 December's issue of IEEE Transactions on Computers. All the paper authors are with the Faculty of Computer Science and Engineering at the Complutense University of Madrid. Our work focuses on thread scheduling for heterogeneous or asymmetric single ISA multicore processors. AMPs have been proposed as a more power-efficient alternative to conventional homogeneous multicores. Specifically, we consider those AMPs that couple high performance out-of-order big cores with low power in-order small cores. Despite the fact that cores in the platform make 7 different microarchitectural features, they all expose a common instruction set architecture. This kind of asymmetric platform I just described has quickly drawn the attention of major hardware players, giving rise to widely spread processors such as the ARM Big Little. In this work, we experimented with 2 development boards equipped with that processor, the ARM Juno development platform and the Odroid XU4 Board. In addition, we had the opportunity to conduct experiments with the Intel QuickIA research prototype, an x86 asymmetric platform which Intel Labs donated to us. On current AMP hardware like the one we used, cores are organized into separate clusters according to its type. Cores in the same cluster share a last level cache and a bus with the remaining cores in the cluster. In addition, all cores share a DRAM controller. Applications running simultaneously may compete for using these shared resources. Despite enormous benefits of AMPs, they actually pose significant challenges to the operating system and especially to the thread scheduler. An important issue is that applications may derive very different performance when running on different core types. For example, in our experimental platforms, applications can run up to 4.7 times slower on a small core than on a big one. When an application runs with others in a workload, this issue becomes critical since big and small cores must be shared among applications. Moreover, contention on shared resources may slow down the execution of an application further. Unfortunately, most default schedulers in general-purpose operating systems, such as the Linux Completely Fair scheduler, do not take these slowdown-related factors into account, leading to highly variable completion times across different runs of the same application. This makes it impossible to deliver fairness, which is a critical aspect in today's computing systems. To overcome this problem, we propose a CAMS scheduler. Its primary goal is to optimize fairness while ensuring acceptable throughput. In this article, we employed a notion of fairness widely used in the context of multicore systems. Fairness is all about ensuring that every single application in the workload suffers a very similar performance degradation as a result of sharing the platform with others. The degradation is measured with respect to the scenario where the application runs alone in the system. In designing CAMS, we wanted to create an OS-level scheme that effectively enforces priorities and does not require hardware support or changes in the applications. Notably, our scheduling approach is the first one that caters to multiple slowdown-related factors on AMPs, including shared resource contention. To even out the slowdown across applications in the workload, the CAMS scheduler assigns each thread a progress counter. This counter reflects the progress the thread has made thus far, relative to a hypothetical scenario in which the thread would have been running on a big core the whole time and in complete isolation. Every time that a thread consumes a tick on a big core or a small core, its progress counter is incremented according to the following formula, which basically depends on 2 things: an estimate of the current slowdown of the thread and the thread's priority or weight. As threads in the workload run on different core types, threads running on a big core typically run faster than threads running on a small one. This is reflected in the progress counters. To even out the progress, CAMS swaps 2 threads when the difference between their progress counters exceeds a certain threshold. To approximate a thread's current slowdown at runtime, CAMS takes into account its current performance as well as an estimate of the performance that the thread would exhibit if it ran alone on the platform with all the big cores available. Devising a mechanism to obtain such an estimate was one of the major challenges of our research, and hence one of the main contributions of this article. To cope with this challenge, we performed an extensive experimental analysis of shared resource contentions on AMPs, which enabled us to draw interesting insights. Based on the conclusions of our study, CAMS leverages a per-thread history table that stores instructions per second samples obtained on a big core in a low contention scenario as the thread runs. To assess the effectiveness of our scheduling proposal, we compare it with other approaches, including 3 fairness-aware schedulers and a scheme specifically designed to optimize throughput. Every scheduler, including CAMS, was implemented in the Linux kernel on top of the completely fair scheduler. To access performance monitoring counters from the scheduler implementation, we rely on the PMC track tool. For the experimental evaluation on real AMP hardware, we considered 40 compute-intensive multi-application workloads divided into 2 sets. These workloads combine different types of single-threaded and multi-threaded programs. The results reveal that CAMS exhibits a fairer behavior than the other schedulers across the board. In particular, our approach is capable of reducing unfairness by 9.5% on average with respect to the state of the art. At the same time, CAMS delivers higher system throughput. To conclude, it's worth noting that the main reason why CAMS outperforms previous approaches is its ability to take into account the 2 major slowdown-related factors when tracking thread progress, including shared resource contention. Note also that our scheduler is highly portable across processor models, as it only relies on a set of runtime metrics that can be easily measured with performance monitoring counters available on commercial AMP platforms. Thanks for watching.